So 7.1, Laplace Transform. So just to start off with, what is a transform? So transforms are just operations that are going to change that function. They're going to transform it, hence the name. So they also have linearity. They have the linear operations that we covered in 4.1. And other examples of transforms are if you take a function and you integrate it, it changes it. And differentiation. So we're going to start off with the definition. Okay, so here's the definition of a Laplace transform. And basically, what we have here is it's a transformation where you have the f of t, function of t, and then once you transform it, it becomes a function of s. Now you can see here it's an integral, and you're integrating that function of t, the f of t, and you're multiplying it by e to the minus s of t. And then after you integrate, again, it's in terms of t because of the dt, but this s is kept constant while we integrate. It's kept constant. But you can see once we've integrated it, it will become a function of s, which is pretty neat, actually. So, of course, that's the definition, assuming that the integral exists. Let's look at some examples. And the first part of this video is I'm going to do a lot of examples. And just like integration, I'm trying to build definitions so that we can pretty much memorize them. Because some of this integration we don't want to be doing every single time. So for our function of t is just a constant 1. So we want to find the Laplace of 1, which means I replace the function in this formula, and it's just 1. So that's the integral of 1 times e to the minus st dt. So we will be good this time and take the limit as b goes to infinity. The definition of an infinite integral is from 0 to b e to the minus st dt. Take the integral, and that's going to be minus 1 over s e to the minus st. And we're going to take that from 0 to b, and the limit as b goes to infinity. So as long as s is greater than 0, that first term will go to 0 because it's an exponential function that's decaying. So just a Laplace of a constant. Well, we all know since the linearity holds with the integral, the c can come out in the front. And we can see we just found this integral right here is 1 over s. So transforms have the linearity property, which means we could have done that from the get-go. That constant can come out in the front, and what's left inside there is 1. And 1 the Laplace of 1 is 1 over s that we found right here. So it's c over s. So putting into the definition, it's f of t times e of minus st. Continuing. So just being lazy there and using 0 to infinity instead of the writing out the limit. So we're going to plug infinity in. We're plugging it in for t. So this is being held constant. So we're plugging it in up here. A is a constant. So that's going to go to 0 as long as s is greater than 0. So here we are going to have to use parts. And if you remember a few videos ago, we did do the gamma function. This looks like the gamma function to me. So let's keep that in mind when we're doing this. Well, it looks similar to the gamma function. And this goes to 0. When you plug in infinity, well, you would have to use L'Hopital's rule. You'd have infinity over infinity, making that going on the bottom. And then you would have 0 over infinity, which brings it to 0. And then you subtract 0, which brings that to 0, minus 0, 0 minus 0. Again, we did that in the last section when there's a very similar situation with the gamma function. And if you recognize this, just like the gamma function last time, there's a function of 1 there. It's the Laplace of 1, which is equal to 1 over s times the Laplace of 1 is 1 over s. That's the first one we did right here, which is 1 over s squared. So our function is t squared. There's the rest of the definition. I'll have to do this by parts. We get u times v. This becomes a plus. And the s can stay out. It's a constant. And again, we just do L'Hopital's twice, because this is from 0 to infinity, and this goes to 0. This, my function is t, so this is 2s times the Laplace of t. And I'm sure we have it here somewhere. Right here is 2 over s times 1 over s squared, which is 2 over s to the third, which will be the same as 2 factorial. 1 factorial. And what about the one before that? 1. 0 factorial over s. Yeah, it still works. Yeah, it works. Fits the pattern. So in general, this is the one to look at. T raised to the n. That looks like it's n factorial all over that 3 is 1 n plus 1. But that is only for n is greater than or equal to 0 and basically a whole number. Because if it's not, well then that's where we have to use the formula of gamma function. So otherwise, the Laplace of t to the n. To remember the gamma function, the n factorial was the gamma. And that's what we'll replace it with. Of n plus 1. And then all over s of n plus 1. So if it wasn't an integer or a whole number, if it wasn't a whole number, we'd have to use the gamma function formula. So if we have the Laplace of t to the minus 1/2, we'll have to basically use this because it's a fraction. So it's gamma of minus 1/2 plus 1, which is 1/2, all over s to the 1/2. And do you remember what gamma of half is? We did it on that last video. It's the square root of pi. So there we get an answer. It's one of those ones you don't want to have to go through and do. You want to memorize it. Do another example. About to the positive half. So again, we have to do the gamma function. You add 1/2. You add 1 to it. Again, we don't know what that one is off the bat, so we could subtract 1. 1/2. Again, I have a gamma video that you can go look up and see why that's so. And then that gamma to the 1/2 is the square root of pi all over s to the 3/2. And it looks better printing that 2 underneath. And there's our answer. So continuing, trying to find our ones we want to memorize. Let's do cosine of omega t. What's the Laplace of cosine of omega t? So that's 0. Throw it into the definition, and let's do the work. So we have to do parts. So that becomes u times v. And we can't forget the chain rule right here. So take the derivative of the angle. I want to box this so it doesn't look like it's coming from there. So I need some more room here. I'm going to move this over here. Okay, so it's uv. And then it looks like we need to do parts again. So this is equal to, so let's calculate this. You plug in infinity and you get 0 there. So that's 0. You plug in 0 in the t, you get 1 there, and then cosine of 0 is 1. 1 times 1. So it's minus 1 over s. And then minus w over s. Now let's use parts. So basically we're just going to do this part. These parts, we already wrote it out. So it's u times v minus, it's this times another minus is plus. But as you can see, so this is my function f with by the definition. This is the Laplace of cosine of omega t, right? That's my function times, that's the definition of Laplace. So just writing that. The ws is already there. Let's go ahead and distribute this though. So that's minus w squared over s squared. And then when I plug in 0 here, I get 0. The whole thing will go to 0. When I plug in 0 here, the whole thing will go to 0. This whole thing pretty much goes to 0. So what's left in front of it is 1 over s, just this one. This is all going to 0. It gets distributed, but it goes to 0. And this is equal to, remember we started off here? So, okay, so our goal is to solve for this Laplace of cosine. So we'll add this to that side. Factor out the Laplace. And what's left? Simplify that. Clear the fraction here. So this 2 times each other. It's just s on top. Distribute that s squared. And there we have it. And again, probably easier to memorize it than to do this every time. We can go through the same exact process. And you can do that as an exercise. It's very similar. But what we get s squared plus w squared on the bottom. But it's omega. Omega is a constant, by the way. And then omega on top. So let's write out what we have so far. So all of these, I think you should memorize all of these, but then go have it in general too. So all of them fit this pattern, by the way. That's a 2 factorial, which is 2. So it's n factorial all over s to the n plus 1. It's an omega on top, s squared plus omega squared. So there's also hyperbolic, sinh omega t, which is omega and cosh. There we have it. So some properties. So given two Laplace transformations of different functions, we have our linear property. And we can basically rewrite it, the plus, as two different transformations. Just like integrals and derivatives, you could do the same thing. And take the constant out. Let's look at a couple examples. We want to find the Laplace of f of t. And we could just substitute it, of course. Just so you know the different ways that you're going to be asked. And so we can separate it like that, break it down. Just do it once, bring the constant in the front. Okay, let's do this. So e to the minus 3t. Oh, we didn't write the e one on here, did we? We'll squeeze it in here. Laplace of e to the at is 1 over s minus a. So this is going to be 6 over s plus 3 plus 1 over s minus 5 plus 7. This one, remember it's 3 factorial all over s to the 4th. And then minus the constant, it's 9 times 1 over s. We could have pulled that 9 out. It's the same thing. There's not much we can do to simplify it, but I'll do a little tiny bit. Not much. 6 times 7 is 42. Another example. So we want to find the Laplace of f of t. So it's basically going to be s squared plus 25. The cosine has s on top. This is s squared plus 25. This sine has the square root of that, which is the 5 on top. So that becomes, it's a common denominator, 3s minus 10 all over our denominator is our answer.